Welcome to the Deep Dive. Today we are plunging into maybe the biggest question out there. What happened before the Big Bang?
It's a huge one.
Yeah. And we're looking at some really fascinating stuff, particularly a new study in Physical Review D, plus some related articles. They're putting forward this, well, pretty radical idea.
It really does challenge the standard picture.
Totally. So our mission today is to unpack this theory, see how it stacks up against the classic Big Bang model, and honestly, just explore the kind of mind-bending places it takes us. Let's jump in.
Sounds good. I mean, it's a question that's always sort of lingered, hasn't it? The standard Big Bang model works incredibly well for describing the universe after that initial moment.
Oh, absolutely. It explains so much, light elements, how galaxies are clustered.
Right, the large-scale structure, all of that. It's been a massive success.
There's still those nagging questions right at the start, like what actually kicked the whole thing off? Why those specific conditions? And the big one, why is the universe so smooth and flat and just enormous?
Exactly those points. And the standard model to deal with those often brings in extra pieces, things like cosmic inflation.
Right, that super fast expansion early on, powered by some field we've never detected.
Precisely, an unknown energy field. And then you've got dark energy later on, another mystery ingredient, needed to explain why expansion is speeding up now.
So it works, but it feels a bit like we're adding patches, using things we can't actually point to.
That's a fair criticism. It leads you to wonder if maybe there's a more fundamental picture we're missing.
Which brings us to this alternative idea from the sources.
Yes, and what's really striking is how it flips the perspective. Instead of thinking about everything expanding out from a point,
it looks inward towards collapse.
That's the core concept. It looks at gravitational collapse.
So not a bang from nothing, but a bounce from something that collapsed first. That feels, counterintuitive.
It does turn things on their head. The proposal is, essentially, that our universe emerged not from a true singularity, but from the rebound after an incredibly intense gravitational collapse.
Like similar to how a black hole forms, but then it bounces.
In a sense, yes. Imagine a massive collapse reaching extreme density, and then, instead of forming an inescapable singularity, quantum effects cause it to bounce back outwards, initiating our expanding universe.
Okay. And the sources claim this isn't just wild speculation, that it uses physics we already kind of know.
That's a key selling point. It tries to stay grounded in general relativity, Einstein's theory of gravity and quantum mechanics, which governs the very small. No need, supposedly, for entirely new, exotic physics.
Which would be a big deal if it holds up, because the standard view of collapse, classically.
Right. Based purely on general relativity, the work by Penrose and Hawking back in the day showed that collapse, like inside a black hole, or maybe for the whole universe collapsing, seems to inevitably lead to a singularity.
A point of infinite density, where the physics just breaks. My brain definitely breaks trying to picture it.
Everyone's does. But this is where the new model brings quantum mechanics into the mix, specifically the quantum exclusion principle.
Okay, I remember that. Like electrons in an atom can't all pile into the same energy level. Two identical particles can't be in the exact same quantum state.
Exactly that. So the theory argues that when matter gets squeezed incredibly densely during that collapse, this principle creates a kind of outward pressure, a repulsive force.
Like a safety valve, preventing infinite density.
That's a good way to put it. As you try to cram identical particles into the same state at insane densities, this quantum rule generates enormous resistance. It pushes back.
So quantum mechanics literally stops the collapse before it hits infinity.
That's the idea. It halts the inward crush and forces it to reverse. That's the quantum bounce.
Wow.
And what this study emphasizes is managing to find an exact analytical solution for this. Not just a computer model, but a precise mathematical description showing how general relativity and quantum mechanics together lead to this bounce.
Why is an exact solution so important here? What does that give you beyond a simulation?
An exact solution means the maths works out perfectly under the rules you've set. It shows the bounce isn't just a possible outcome under specific simulated conditions, but a direct fundamental consequence of how gravity and quantum effects interact at that scale, according to the theory. It offers deeper insight.
Okay, got it. So collapse, quantum pressure pushes back,
Yeah.
no singularity, we get a bounce.
Okay.
But what kind of universe emerges? Does it look like, well, our universe.
And this is where it gets really compelling. The theory suggests the universe that comes out of this bounce naturally has features very similar to the ones we observe.
Mm-hmm.
And it does this, potentially, without needing those extra ingredients like inflation or dark energy.
Wait, how? How does the bounce itself explain things like that accelerated expansion?
It comes down to the physics at the bounce point. General relativity connects space-time geometry to density and pressure. At maximum density, the quantum effects supposedly create not just immense energy density, but also a very large negative pressure.
Negative pressure.
Yeah, it's a concept from relativity. And this specific combination, arising naturally from the quantum gravity interaction at the bounce, mathematically acts like the vacuum energy or cosmological constant that drives accelerated expansion.
So the bounce itself creates the conditions for rapid expansion.
Exactly. It inherently generates two phases of it. An initial burst right after the bounce that smooths and flattens things out, much like inflation is supposed to do.
Okay.
And then, the theory suggests, residual effects from that bounce mechanism also drive the slower, late-time acceleration that we currently attribute to dark energy.
Whoa. So instead of adding inflation and dark energy as separate things, the bounce mechanics produce effects that look just like them.
That's the proposal. They emerge from the known physics interacting at that extreme moment, not from new hypothetical fields or energies.
That would be
Oh.
elegant, if it's right. But okay, the big question. How do we test this? Ideas about before the Big Bang are notoriously hard to check.
And testability is something the proponents really highlight here. They argue this model makes concrete predictions about the universe today that we can actually go out and measure.
Okay, like what? What should we look for?
One of the main predictions is that our universe should have a tiny but positive spatial curvature.
Spatial curvature. What does that mean in simple terms? Like the universe is shaped like a ball.
Sort of, yeah. Think about geometry. On a flat sheet of paper, triangle angles add up to 180 degrees. On the surface of a sphere, a positively curved space, they add up to more than 180. This theory predicts that on the very largest scales, the geometry of our universe is slightly positively curved, like being on the surface of a truly gigantic sphere, not perfectly flat like standard inflation predicts.
And we can measure that. How?
Through precision cosmology. By studying the patterns in the cosmic microwave background, the Big Bang's afterglow, and by mapping the distribution of billions of galaxies over cosmic history. These let us probe the overall geometry of space.
And this slate curve, if it's there, would be a leftover sign from the bounce.
The idea is it's a relic signature, perhaps linked to the slight overdensity that might have kicked off the initial collapse way back when. It's a specific prediction that differs from standard inflation.
So new telescopes and surveys could actually find this or rule it out?
That's the hope. Missions that are coming online soon, like the European Space Agency's Euclid satellite and another one called Arrakis, they're designed to make exactly these kinds of high-precision measurements.
Wow.
So in the next, say, 5 to 10 years, we could genuinely get data that either strongly supports this bounce idea or tells us we need to look elsewhere.
That is genuinely exciting, to think we might get clues about the very beginning relatively soon. Now, the sources also mention connections to other big mysteries. Black holes, dark matter. How does a cosmic bounce link to those?
Yeah, this is more speculative, but very intriguing. The extreme conditions during the bounce incredible density energy might have been perfect for forming what are called primordial black holes.
Black holes formed right at the beginning, not from stars collapsing later.
Exactly. And if the bounce created a population of these primordial black holes, well, maybe they acted as the original seeds for the supermassive black holes we now see in the centers of nearly all large galaxies.
So the bounce didn't just start the universe, it might have planted the seeds for galaxies too.
It's a possibility. It could help explain why those supermassive black holes got so big so early in cosmic history.
That connects a few dots. What about dark matter?
Well, here's another leap. If these primordial black holes were produced with the right range of masses and in sufficient numbers during that bounce era, could they be the dark matter?
Wait, the dark matter we've been searching for decades could just be tiny black holes left over from the bounce.
It's an idea that's been around, but this model might provide a natural mechanism for creating them in the first place. It's a very efficient way to potentially solve two massive problems at once: galaxy formation seeds and dark matter.
Goodness, that ties a lot together. Still speculative, you said, but
Highly speculative, but it shows the potential explanatory power. And missions like Arrakis, which will study faint stellar halos around galaxies, might find subtle clues about how those galaxies formed, maybe pointing towards or away from this kind of primordial seeding scenario.
Okay, let's get to the part that really messes with my head. The implication that if our universe came from a collapse, maybe inside a black hole, in some parent universe,
Yeah.
then we are living inside a black hole.
Yeah. That's the most profound and perhaps unsettling takeaway. It reframes everything.
It really does.
The Big Bang stops being this absolute beginning ex nihilo from nothing. Instead, it's a transition, a continuation from a previous phase.
A rebound.
A rebound, exactly. The universe didn't just pop into existence. It transformed from an earlier, ultra-dense state.
So maybe existence didn't start with our Big Bang. Maybe it's cyclical.
That's the ultimate philosophical implication, isn't it? That we could be part of an eternal cycle of cosmic collapse and bounce, governed by the fundamental laws of physics, gravity, and quantum mechanics playing out on the grandest scale imaginable.
And the weirdest part is you're saying this isn't just like poetry. It's emerging as mathematically plausible from the physics we know.
According to this research, yes. Applying established physics to those extreme conditions leads to this possibility. It moves the idea from pure sci-fi towards something potentially describable by equations.
It just completely shifts how you view, well, everything, our place in it all.
It really does. We go from being the result of a unique, singular creation event to potentially being just one phase in an unending cosmic dance between gravity and the quantum realm.
Okay, let's try and wrap this up. This black hole universe, or cosmic bounce theory, it's a really fascinating alternative story for our origins.
Definitely compelling. And its big draw is that it attempts to work within known physics, relativity, quantum mechanics.
And it potentially solves some major puzzles of the standard model, right? Like explaining those periods of accelerated expansion without needing to invent inflation fields or dark energy.
Yes, suggesting those arise naturally from the bounce dynamics. And crucially, it makes predictions we can actually test.
That small positive curvature.
Exactly. Something upcoming missions might be able to detect, or not, in the coming years. That gives it real scientific weight.
So the really big thought to leave everyone with is this possibility that our universe wasn't born from absolute nothingness, but rebounded. Maybe from inside a black hole, maybe as part of a cycle. The beginning wasn't a singularity, but a bounce. It makes you wonder if we're not at the start of time, but just riding one wave in an eternal cosmic ocean. And the next few years of data might just give us our first real clues.